Science and Technology Innovation Program here. And this is a program on the use of algae to deal with climate change challenges. I'll give you just some of the backstory. In April, I spent 2 weeks at the International Institute for Applied Systems Analysis, which is just outside Vienna. For those of you who don't know about IASA, there's some material out on the table there that'll give you some of the history, but it's a very intriguing result of science diplomacy during the height of the Cold War that was done by the US and the Russians to create a place where scientists from the East and the West could actually meet and exchange information. And it continues to survive and really thrive today. When I came back, we actually put an MOU in place now between IASA and the Wilson Center. And this is actually our first combined meeting. When I was over there, I gave a talk on synthetic biology, and as I left the room, one of Brian's colleagues, Michael, sort of cornered me in the hall, and he had this paper he wanted to show me. So he sat me down and said, you got to see this paper because we're actually running a global model using synthetic biology. And I was quite fascinated by this because quite often you don't see many papers that actually try to model the impacts of emerging and disruptive technology at a global scale. And that's what this model is doing, and Brian will explain it a little bit. The other thing is it's an integrated systems model, so it's looking at energy, food, and land use. And I think when you integrate like that, it opens up some possibility spaces that you just don't see if you're just modeling within silos. I think that was the other thing that's quite interesting. And the third thing that was quite mind-boggling is under some scenarios, the model says that we can actually bend the temperature curve of the planet down below 2 degrees centigrade by 2100. So if you watch the recent news, we've kind of given up on that goal. People are talking about 3.5, 3.6 degrees centigrade. So the more I looked at it, I said, this is a paper or a model that needs to get greater attention. And so Brian's been here at the algae bio meetings, and we've also decided to have him come and just talk and present the model. So he's going to go through the model, and and then we've got a bunch of people to respond. Jill is from Solazyme, so Jill's company actually makes synthetically engineered protein, and is actually looking at this is a market. So we.
Our protein is a native algae.
No, native
Yes.
algae. Okay. So.
Yeah.
So you just basically, this is kind of one of the inputs into the model. David's from the Union of Concerned Scientists. He's a civil engineer. He's done a lot of work on biofuels. And Jennifer Turner is a colleague here who actually does a lot of work on, they have this report here, Water, Energy, Food Roadmap for China. China's obviously a huge consumer of protein from around the world, including the US. So what we're going to do is have Brian go through the model and kind of take you through the assumptions, what he's modeling, and then have each of you kind of talk a little bit about your response to the model in terms of, about the approach, the assumptions, things that you'd like to see in the model, since this is malleable.
Yeah. Yep.
Obviously, one of the things IASA is looking for is, can they change the model, build out more? They've got models that they could add to the large integrated model. How could we use the model to sort of impact the policy debate? And obviously potential critiques, pointing out holes in the model, things that would be good to change or get tighter in terms of the modeling. And we've got, I think, copies of the presentation. A lot of this is in a paper that's going through a peer review now.
That's right. That's
so
right.
Hopefully it will be published soon, and you'll be able to have a reference for this. But I think at this point in time, it was great to actually get this in front of people to sort of react to, and that's one of the things that we wanted to do in inviting Brian. So I'll turn it over to you. Why don't you go through the model and kind of what you found out.
Okay. And I'll say now, and I'll.
Brian, just use the mic.
Yeah, can you use them?
You may want to.
Can we give him a hand mic?
Should I sit?
We'll give you a hand mic if you
You
want.
can do that.
You control the room better
Yes,
standing
that'd
there.
be great. I'll say now, and I'll remind you at the end. The model also has a website so that you can, so people can sort of look at it and probe it and see, what holes are there, and to encourage maximal transparency. So the model it's Felix, felixmodel.com, Felix, and that'll be written at the end. So as Dave said, I'm Brian Walsh. I'm a research scholar at the International Institute for Applied Systems Analysis, which was not named by a marketer. But I'm here to present a study that we've been doing in other rooms. It's called New Feed Sources Key to Ambitious Climate Targets. But today I'll call it Show Me Your Pathway, to quote Professor Jeff Sachs. And so we've got a relatively diverse group, mostly Europeans, I guess, and we've been working with some Australians as well to look at this. So I'm going to just walk through a few scenarios today to actually see how to construct some pathways for emissions reduction. But I want to begin by introducing Felix. Felix is a systems dynamics model, which means it's linear differential equations, and it is in fact global in scope. So it's got demographic, economic, land, food, energy, and carbon sectors, and these are all interlinked. And the goal of the model is to assess impacts of policies and today technologies relative to business as usual scenario, relative to a baseline. And these are global scenarios, so we don't have any sort of geographic explicitness, but we do get to look at where megatrends headed and you know what does a successful pathway look like. The model is calibrated. The power of the model is that it's calibrated to historical data. It integrates data on population from Indesa, on economic development from the World Bank, food and feed from the FAO, as well as land, and energy, global energy profiles from the IEA. And so these are independently impressive data sets, but you know, it's not clear how they hang together. And the power here is that we can actually begin to look and we can discuss linkages and presumably always improve. And then ultimately, as today in many scenarios, the results, what we're looking at is emissions pathways and profiles. And so we validate these results with CDIAC data and IPCC representative concentration pathways, which are sort of global baselines for future development and future development and economic and demographic development. So I call this Show Me Your Pathway because we at IASA some people are environmentalists at heart, or maybe most are, but we are agricultural and resource economists by training. And so a person can walk in and say, I don't want to see nuclear, I don't want to see GMOs, I don't want to see anything. And that's fine, but at the end of the day, we need to meet climate targets, we need to meet food production targets, we need to meet all of this, a host of things. And so I'm going to construct pathways which are not business models and on which nobody can make money, but which may actually have a really significant impact. And so there are really just 3 steps to this. First, we're going to talk about the problem. We're going to talk about business as usual in the Felix model, and I think it's representative of where we're headed, and the model goes through 2100, so you can take everything with a grain of salt, I guess, but the business as usual assumes no transformative technologies, just we continue on the track we're headed, historical trends expanded into the future, and let's see what we need to do to get away from that. Then I'm going to look at partial solutions, renewables, and carbon capture and sequestration, and look at how far those can take us, and where do they fall short. And then we'll talk about algae as the potential missing link, as the key to sort of solving a number of problems simultaneously. So the problem that we're facing is really quite simple, and it's called the global carbon budget. And this is the question from which we start is, how much carbon can we, being civilization, emit while still limiting warming to 2 degrees Celsius, less than 2 degrees Celsius? So for the moment, we're going to set aside biodiversity, we'll set aside ocean acidification, we'll set aside all that, and we'll define success just as keeping the global temperature under 2 degrees Celsius. And the 2 degrees is a nice round number, and maybe some people are giving up hope, but a lot of people think that actually 2 degrees is already not ambitious enough. And I've got another nice round number here. The global carbon budget for civilization is 1,000 petagrams of carbon. And this number doesn't necessarily need to mean a lot to you, though 1,000 petagrams, it may stick in your head. But it should mean something when I tell you that you are here at 500 petagrams, cumulative emissions from civilization. So in the last 150, 200 years of industrialization, we've blown through half of our budget. And alarmingly, we're on track to run through the rest of our budget to the remaining 500 petagrams by 2060. So in just 45 years or so, we will have committed ourselves to at least 2 degrees warming, if not more. And you can see the curve just goes up and to the right very alarmingly. And I'll say now that everywhere you see a shaded region, this is Endesa's high and low population projections for through 2100. So that's one of the leading sources of error here. And so you can see what is the effect as for high and low estimates. And when we start to dig into that emissions trajectory, we can look at annual emissions. So here we have annual net emissions. And the question that I live in Europe, so maybe you think that I've come back as an alarmist, a climate alarmist, and that this is just the worst case scenario, and we don't have to do anything, or marginal improvements will make a difference. But in fact, it's not the case. So the business as usual scenario here forecasts a 25% increase in 2100 in annual emissions over 2010 emissions. And that's by no means the worst case scenario. So the red dotted line here is the IPCC's worst case scenario. And that is that forecasts emissions continuing for the next 40 years or so at the historical rate of increase. And so at that, and eventually leveling off because of population growth and or famine. But what happens there, so there we get to, in the worst case scenario for the IPCC, we see emissions 3 times what they were in 2010 and well over twice what they are in the business usual. So this is no worst case scenario. It's relatively middle of the road. And when we dig a little deeper, of course, we need to talk about where is our energy coming from moving forward in order to add up to that amount of emissions that we're foreseeing. And so, again, to reinforce the fact that this is by no means the worst case scenario, I show our primary energy profile here for global energy consumption in the business as usual scenario. And you can see that in 2100, the market share of fossil fuels has dropped from about 95% where it is today to 60%. And that is a 20% increase relative to 2010 in total fuel consumption, which is a function of the demand growth. And in this case, the remaining 40% is renewable energies. And so specifically in the business as usual scenario, this is just assuming, let's keep going as we have been. We're looking at 215 times growth relative to 2010 in wind energy, almost 40 times growth in solar production, and 11x in biomass. That's 2100 over 2010. So, I think for some people that would count as success in the renewables market. But returning to our emissions profile, it's still the case that we're up at 12 petagrams of carbon per year. We're far exceeding our global carbon budget, and the energy sector in this scenario still accounts for 80 to 85% of anthropogenic emissions. And then land use change, which is specific land use and land use change, agriculture and deforestation, is accounting for another 15 to 20%. But you can see that it's almost doubled in 2100 relative to 2010. That's the gray at the bottom there. So something's going on under there, and I'll again remind you that we have to get this pathway down significantly. And when we look at our gross emissions profile, you begin to see there are 2 mitigation options that are frequently discussed and which are almost sure to be part of our energy future. And the first is carbon capture and sequestration. So we'll talk more about this a few slides from now, but CCS for short is the liquefaction of carbon emissions from fossil fuels and from biofuel plants. And these are subsequently pumped underground, hopefully permanently. And this is a feasible technology. It sounds maybe like science fiction, but it's real and it's already happening. And it's certainly going to be part of the future. And that can tackle emissions on the top side. And then renewables are another option, and certainly one on which we need a lot of work. But you can see the pathway going down is the sequestration in forests, in energy crops, before the biofuels are burnt. And of course, this is a net carbon positive process, as is everything, because it takes input, but it significantly offsets the total emissions. So this is going to be part of a climate safe future as well. Okay, so that was business as usual, and now the question is, what really is an acceptable pathway? Where do we need to be by 2100? And the answer is this green dotted line at the bottom. The IPCC says that we need to achieve net zero anthropogenic emissions, if not negative emissions, by sometime around 2075 in order to keep warming under 2 degrees Celsius. And that is really an enormous task. I think that's already clear. But this is the only acceptable pathway if we define success as under 2 degrees global warming. And to reemphasize that point, I'll just show you that this is temperature change, global temperature change over pre-industrial in degrees Celsius. And you can see where we are. We're right around between 0.7 degrees and 1 degree Celsius. We're on track to rise above 2 degrees around 2050. And by the end of the century, we're looking at 3 degrees Celsius. And then the IPCC, the consensus estimates for the green dotted line that I showed you, the low emissions pathway, they range from between 1 and 2. And in the worst case scenario, we can be well above 4 degrees Celsius, if not 5 degrees Celsius at the end of the century. So for the last time, I'll say that 2 degrees was chosen because it seems to be the point at which we could live with climate change, and at 4 or 5, it's sort of all bets are off, and certainly my model needs to be scrapped. So that would be an entirely different world. So this is where we need to be, low emissions, the green pathway. And so now let's look at these partial solutions and see why are they important, but where do they fail us? And so I will start with renewables. And so let's one thoughtful response to the energy profile would be to say, well, what if we really pushed hard on these? How far could we possibly go if we drove renewables? And so in this scenario, fossil fuel consumption has fallen by about 1/3. So it's 40% of primary energy production, and that's a 10% decrease relative to 2010. So by the end of the century, many people would consider that phenomenal. In this scenario, 60% of our energy now comes from renewables, and so that's almost a factor of 400 increase in wind, 70 in solar, and 15x in biomass, up to 190 exajoules. So this, again, maybe it sounds great. Maybe this is us on the right track. But when we start to look at the benefit, even this extraordinary scenario gives us a 20% emissions reduction in 2100 relative to the business as usual. And obviously, this is far short of our goal. There's enormous room for growth, and it's clear that no amount of renewables will actually get us there. And when we look at our carbon budget under this scenario, we've pushed our deadline from 2058 to 2061. So I guess that counts as success in Washington on a budget, but it is definitely not the case. Globally, it's within the margin of error. And so there's no effect here, and it's not to say we shouldn't push, and certainly renewables are a big part of our future, but it's simply insufficient. So those are the benefits, such as they are. And then we begin to look at the cost. So we can see the major costs here is deforestation and habitat destruction. The amount of bioenergy that I forecast, 190 exajoules, it does include agricultural residues. It does include energy crops insofar as there's land available. But actually the burden falls on forests, natural forests. And this is something we've already seen in the context of EU biofuel targets. It drives deforestation in the southern hemisphere, and that is forests we can't afford to lose. So when we talk about 190 exajoules, we're talking about 400 million hectares of plantations, managed forests. And that is 10% of current standing forest stock. And so the model does incorporate the land use change, the emissions penalties for that, but which are significant. But what it doesn't look into is the food and feed demand, the food and feed price increases that come as a result of this, competition for arable land, and actually energy crops are not likely to be a significant contributor moving forward. So forests are going to take the burden of this. So that was the cost. That was the cost of the biofuels pathway, but still, it's necessary. But I'm going to cross it out for now because it's not going to get us there. So we can look at carbon capture and sequestration, which again is carbon emissions liquefied and pumped underground, presumably permanently. This is expensive, certainly, in terms of capital investment as well as in terms of energy. It costs 20% of energy, the energy output of an individual plant. But it is technologically feasible, and increasingly it's clearly going to be a part of US and global energy future because, for example, even just now, the new emissions limits for coal plants will almost certainly require that CCS is put on top of new coal plants. But it's easy for us, anyway, to imagine this. So let's use CCS to reduce emissions from the entire energy sector up and down by 25, 50, or even 75%. And by the way, please stop me if I'm going too quickly, because I'm not used to diverse audiences, only modelers usually. Okay. But when we're looking at CCS, here again is our pathway, the annual emissions, and again the green dotted line shows the target. And what you can see is that once you dig down to about 75% emissions reduction due to CCS, and I'm sorry, by the way, I've banked the 20% reduction with our renewable scenario, and these reductions are put on top of that profile that I showed. So 25%, nowhere near. 50, nope. 75, 75% emissions reduction for CCS, we've gotten there. But this is no mean feat. First of all, CCS implies to the entire energy sector, so every coal plant, every natural gas plant, every biofuel plant worldwide, and certainly it means that we can no longer use conventional fuels for cars. It means electrification of the entire energy sector, and only then could we imagine achieving such a mitigation. The magnitude and the cost of the infrastructure is, again, this is going to be something in which we're investing already. Carbon is liquefied and pumped around the United States in order to, in the process of fuel extraction. So, there's some overlap there, but the infrastructure is an enormous penalty. And it's not clear that there's enough permanent storage capacity. So this carbon is being pumped deep into depleted gas and oil reserves, as well as presumably aquifers moving forward. And this, but we don't know really how much is there. And so this would be a real Hail Mary if it came to that point. Okay, but there's one more that I've not talked about and which brought you here, and it's algae. And algae goes to the heart of the question, because the question is actually how are we deploying our natural resources? I've talked about land scarcity, and none of these things do anything to address the land scarcity that actually that links food prices, that links energy, that links water, and which links the carbon system. So algae may be the missing link. And I am not an engineer, but I've spoken with engineers, and I first want to add the disclaimer that we're going to be talking about a system which is 4 to 5 orders of magnitude larger than currently exists. But so I'll say that right now, and that's clear. But algae has already achieved enormous productivity. So talking about closed phototrophic systems in the Benelux region, in Belgium, Netherlands, Luxembourg, they've achieved 150 tons of dry biomass per hectare per year, which is 2 orders of magnitude better than we can do with soy or corn. And so this is not limited to the Sahara. This is happening in the Netherlands with the cloudy continental climate. And there's enormous productive potential here. Really, essentially, these systems can be built on degraded or unproductive land. So all of a sudden, we're decoupling this production system from food production systems, from traditional bioenergy production systems, and it can be done in salt or brackish water. So all of a sudden, we can build these systems, and there's minimal freshwater cost. On top of this, it can be fed with flue gas. In many cases, this is the limiting factor already for global production systems of algae. And so at the beginning, we're going to have co-location, but flue gas already is an important factor. And it can be fed with wastewater. Wastewater is a sort of unheralded crisis, I think. Wastewater and the nitrogen and phosphorus fertilizers that it carries away is really the next looming challenge that I think we don't talk enough about. But algae has the potential to close these cycles, to close the carbon, the water, and the fertilizer cycles in a way that sort of gains maximum productivity out of all of these. And so there's at the very least the potential. There's the enormous scaling challenge, which I'm just going to set aside for the moment conveniently. But algae has the potential to avoid the trade-offs and the problem shifting that we see with all of with first and second generation biofuels, with all the other solutions that we talk about on a daily basis. And this makes it a compelling technology if you're looking at the holistic perspective. It's not, I set our focus narrowly on 2 degrees warming, but in fact, from a much larger perspective, this is really an area that deserves a lot of close scrutiny. And so I want to take a step back from emissions pathways for a minute to go into the food and feed sectors of the model. And what is happening, I guess, is that we're facing a greater than 100% increase in animal food demand, let's say animal calories and animal-based protein, over the next 90 years. So over here we got a 117% increase, to be precise. Contemporaneous with that is an 82% increase in vegetal food demand. And this is the combined effect of population growth as well as economic development as economies come online and hunger for meat grows worldwide. And so to cut straight to the chase now, here's the pathway. We can certainly imagine a world in which we use algae to offset feed demand. Oh, I think I skipped a point there. But we're going to go big. 35% of animal feed demand worldwide, let's imagine it's met with algae. And this is perfectly conceivable because it's been shown that studies have shown for decades now that cows and pigs will eat up to 35, 40% of their diets can be algae without any effect on animal growth rate, animal mortality. There's no effect on food palatability whatsoever when it comes to this. And And what does that look like? What's 35% of global feed demand? Well, it's half a gigaton of biomass in 2010, and it will be a full gigaton of biomass in 2100. And that's, of course, no small order, and I don't mean to suggest that this would mean feet, except when we look at what area would it actually take to do that. We're talking, this is for 1 gigaton, we're talking 10 to 25 million hectares, assuming a rate of 100 to as low as 40 tons of biomass per hectare. And that, to put it in perspective, the area of pasture in the United States alone is 250 million hectares. So you're talking 1/10 of the pasture area of the United States. The arable land in the United States is 150 million hectares. So this is a small fraction. I mean, the U.S. is a small fraction of U.S. agricultural area, and that would be enough area to feed the entire world or meet this level of demand for the entire world. And why would we do that? To look at land again, this is now global, not United States. We're currently using about 5 billion hectares for agriculture, and that is 5 out of the 7 that exist that we have been identified as arable so far. And of that 5 billion hectares, about 25% is used for food production. The remaining 75% goes to the production of animal feed. And so this is actually, and of course I told you that we're facing a doubling of animal demand as well as 80% increase in food demand. And so while it's reasonable to expect that food yields will increase, they're not going to increase. They're not going to increase. They're not going to keep pace. It's not 1 for 1. And so we can project that we'll be looking at 5.7 billion hectares by 2100. This is about a 16% increase. However, if all of a sudden if we started to use algae to meet that demand, then all of a sudden we've just freed up 1.7 billion hectares of agricultural arable land worldwide. 1.7 billion hectares is a sort of unfathomable number, actually, but this is the power of the productivity of algae. It's quite singular, and this is where it becomes a compelling story. So what would I have you do with 1.7 billion hectares? I would begin by addressing the land shortage and the limitations that we discussed on biomass production worldwide. So, of course, as I said, algae itself and biofuels, they're carbon neutral or marginally carbon positive. But this is really essential because from the beginning, we're constructing an enormous area of biofuel production plantations without competing with agriculture, without driving deforestation, and without placing stress on municipal and agricultural water supplies. I just suggested we spend 1.1 billion on biomass production, but we had 600 million hectares left over, with which we avoided grassland and other habitat destruction. So this is a hidden cost. Grassland, the emissions associated with grassland and grassland change is actually another sort of factor that gets ignored because it's not carbon rich, but certainly it's biodiverse, and it's a very important part of many ecosystems. So now I want to go back. This was my renewable scenario, our renewable scenario. This is where we were. 43% of our primary energy supply came from fossil fuels. Now, once we've put those 1.1 billion hectares into production, we can see a 3 times increase over the renewable scenario in our biomass production. And so, of course, this should be pretty astounding, but especially because fossil fuels in this scenario fall below 17% of total energy consumption. We've phased out oil consumption entirely, gas is a little bit of that, and coal as well. But we have avoided an enormous amount of land use change and deforestation and the emissions associated with that. So back to the pathway. This scenario alone, even that level of biofuel production, if you'll believe me, I hope you do, is far short of what needs to be done to stabilize carbon in our atmosphere. We've achieved a 45% emissions reduction relative to 2010, and this is still far from enough. But when we bring carbon capture and sequestration back into the fold, all of a sudden we now see for the first time the possibility of deeply negative net anthropogenic emissions. And so I'll just zoom in on this plot. And you can see even when you get down to 25% efficiency, which is far lower than any plant that's operating would actually run. They'd easily run about 40%. And you can squeeze gains out up to 50% relatively cheaply. You can see that let's start at 50%. We've achieved a deeply negative emissions pathway, and we've done this. This went negative because of the renewables that we're consuming. Biomass in its growth process pulls the carbon out of the atmosphere, and when we burn it, instead of releasing it back in a one-for-one process, we apply carbon capture and sequestration and lock that away. And so that's how we get to deeply negative emissions. So this is a plot of atmospheric CO2 concentrations, and 300 is pre-industrial. And you can see that at 25% efficiency of CCS, you can achieve stabilization of atmospheric carbon. When you go to greater capture efficiencies, then that's where we get to pre-industrial carbon levels. And I will end. So here's sort of the exciting plot. When we go that deeply negative, we can actually return to 1 degree Celsius before the end of the century, subject to the smaller range is actually other greenhouse gases. So these are included as well, and the larger one is the productivity of the plantations that we've been looking at. So we look at a wide range there. And I want to remind that even though we've not discussed it today, we've addressed this without putting enormous burden on water cycles. We've done so, and we're closing nutrient loops that are just leaching into the oceans and driving biodestruction, I guess. So in this case, I mean, going back to a systems perspective, algae is actually potentially a magic bullet when we're talking about the Sustainable Development Goals in the context of the SDGs, for which it's been suggested that there's a $4 trillion price tag on each of the 17 SDGs. This starts to look like a really nice way to wrap all of these up and address them simultaneously. And with that, I'm going to stop after I put in the obligatory plug for IASA. And we have, I don't know if you or anyone you know is a senior grad student, then we've got a Young Scientist Summer Program for you, the goal of which is a publishable paper at the end of the summer. And if you or anyone you know is a postdoc or looking to be one, IASA has a 2 years postdoctoral program with rolling admissions, and literature is in front in case anybody's interested. So I'm going to turn over to the panel, and I want to thank Dave and Todd for organizing this, as well as Aaron, if he's still here. And here's my contact information, as well as the website for the model, so that you can look and we can continue the conversation. Thank you.
Okay, thanks for taking us through that. So just some questions. I'm going to start with you, Jill, and then I know David's marked up the paper, so he's probably got a whole bunch of assumptions.
I won't ask him here.
One of the things that struck me when I first read this paper was this assumption that we could substitute 35% of the protein as presently being fed to ruminants and poultry. I mean, do you think that's realistic, and how long would it take to scale to that?
Right. So I don't know if it's per se, I don't know if the replacement of 35% is considered all protein, because when you look at animal feed, it's a variety of nutrients that are in there. So there's been a study published about work done on the algae meal product produced from Solazyme's algae. And that's one of the papers that you cited, and it looked at you could be up to 45% use. It's not necessarily all protein, but it's the combination of nutrients that you could displace some of that corn. So we've seen it, we've seen that being played out actually in research directly on the algae meal that we're making. And I should just be clear, our company makes oil and other products from algae in a closed fermentation tank. So it's a different production process than what you're talking about, but you're asking about the very specific, can it work, right? So when we squeeze the oil out of the algae, the leftover algae meal is what we are using as animal feed. So I just want to be clear.
In terms of you had the example there from Luxembourg or wherever it was, and in terms of what's
150 tons biomass per hectare per year.
right? And is that something you think?
Yeah,
Our
you know what,
system.
I don't even know. I'd have to look at that. I haven't even looked at those kind of figures for us. I think about it as oil, right? So I
yeah.
don't think about it as biomass, but we can get back to you on that.
I think you can scale this, keeping it inside fermentation tanks, or at some point in time would you have to go into open systems?
Well, it definitely can scale, absolutely. I mean, fermentation's been a process for hundreds of years. It's a very known process. You just keep doing more of them. So that's, and we're scale now. So the question is, what are the impacts of scaling, right? I think that's the question, and how does that compare to scaling with ponds?
Okay. So Jennifer, China, whenever we have discussions about protein, it's always this, are all our soy futures going to be sold to the Chinese? And
Yeah, I mean, well, China is, that sound of the whoosh of soybeans moving around the world. I mean, 60% of all the soybeans that are being tossed onto the global market are going to China. I mean, something about, is it fair? I have to make sure I get my numbers right. I know that that half of our the U.S. ag exports to China are soy, and that's 11% of the U.S. trade. And so, I mean, on a side note, it's not directly, I mean, I was thinking, wow, the ripple effects that if you started, not that you couldn't replace the soy right away with this, but, and I guess maybe the scaling up of ag and the lowering of soy. But I mean, it's a solution that's needed. I mean, I passed out the infographic, my great pork infographic that shows you that meat consumption in China is growing. I mean, China's the world's factory. The cities are booming. The people are getting richer. They're eating more meat. Still per capita, it's only about a quarter of what we in the U.S. eat. I'm a vegetarian, but you know what I mean. What we Americans eat in terms of meat, and and the hunger for meat is only growing. I mean, they're building these factory farms, along the coastlines, and it's not just pigs; it's also chickens. Chickens actually need more soy per kilogram of meat than the pigs. So I mean, so the demand is great, and so I could see that this is something that, I mean, China, but even thinking domestically, the food that that the crops they use for their own product, for their own food production, it's very limited. They have limited water and limited land, and I was kind of curious about, if I can ask him a question about the water, because you said that this algae can be developed with wastewater, and I keep thinking in China about 30% of China's water is so polluted it shouldn't come in contact with humans, right? A lot of heavy metal in their soil and their water, and I was thinking, like, would I want my algae that's, but tell me about that. Polluted water, growing algae, does that get into the food chain at all? Sorry, it's a naive question.
No, not at all. I think it's really important. And so this is, it's not clear, actually, I would say, how much of the metals are actually taken up into the algae production. What is clear, and specifically in the example of China, I mean, China's dumping about 4 times the amount of fertilizer that any sort of growth of crop could possibly take up onto sort of hundreds of millions of hectares of land. And so there's enormous amounts of nitrogen and phosphorus fertilizers running off, on a scale that we don't see anywhere else in the world. And so for China, if, while there is risk when it comes to polluted water and heavy metals, there's also enormous value actually in that wastewater in the form of these fertilizers that are leaching and running off.
And even also saying, politically, I mean, a few years ago, China, they came to terms with the reality that they could not have food self-sufficiency anymore, right? I mean, they'd been importing lots of grain, because importing grain for China is importing land and water. But still, being so dependent on imports it makes them nervous, right? It's a food security issue for China. And so that's why I could see that, I have no idea how soon you can scale it up to the sense where the, Chinese government gets super excited. But I think politically, there'd be a real big interest in this. I mean, around the world, but China, and again, what it's doing, the deforestation from soybean production. I mean, you were just talking about that, huge.
So David, any sort of general responses, questions? I mean, one of the other things that came up when we had this discussion with Brian is just this issue of carbon capture. And just how realistic that is. I mean, do we have to co-locate, the algae with next to carbon sources and stuff like that?
One of the interesting things with respect to CCS in this particular paper is that the amount of CCS that would be necessary for some of the, for achieving our carbon goals is extensive, and there would need to be co-location. First of all, the type of algae that's modeled in this paper are autotrophic, those that take up CO2 directly. So this is a different model than what Solazyme works with. These algae do need to be co-located. I think, and CCS is, a lot of modelers are recognizing that it's going to be a significant part of our strategy to address climate change going forward, even under high biomass utilization scenarios. That's how you get the negative reductions. The one thing I would say as a general comment, and from my position at the Union of Concerned Scientists, from a policy standpoint, what kind of comes out from this paper, not the specific end goals, like what is the temperature reductions that we could see, or the final concentration of carbon in the atmosphere. But what this paper really highlights are the differences between the scenarios that you present. And what this suggests is that we actually need to view autotrophic algae production on a large scale as a feedstock for animal feed rather than for fuel.
Yeah.
And the incentive structure around agricultural feedstock production, including algae production, has been largely around producing fuels from these things. And so the question really is, this paper presents, what we need to do with this feedstock, and now it presents a policy challenge of how do we develop incentive structures to actually achieve the climate goals that we want, right? The incentive structures around fuels were there to address climate emissions, but it looks like we could get more climate emissions out of using this feedstock in the agricultural sector. And so how do we get an appropriate price on carbon and an appropriate incentive structure to actually begin directing these types of feedstocks into the agricultural sector? So that's a huge takeaway, regardless of, we can quibble about the assumptions that you make and the final results of all of these things, but the real differences between those scenarios is I think, the biggest finding in this paper, and presents that question from a policy standpoint. How do we do it?
Okay. So Jill, I mean, this is obviously, at some level, it could be a big business opportunity, right? I mean, what kind of barriers do you see, as a business, just to get in here? I mean, is it a policy issue? Is it a market issue? Or is there public perception issues about, obviously, we talked about, you're not feeding this to humans, but what do you run into in terms of barriers if you're trying to scale your business?
Right. I'm going to talk about two things. First, I want to just say, I think one thing that's also in reflection on what David said in terms of the concept of less is more, the idea that that we can make out of less land and resources, we could actually provide more products, for what we need, as with the growing population. And so when I read it, I kind of thought about, wow, I think about when we are producing our algae, again, off of 1 hectare of sugarcane, because we feed sugar to our algae to make oil and the algae meal, we're making an energy source because of the sugarcane, we're making oil, and then we're also making an algae meal product. So the idea is, do we have multiple ways to use that acre of land to make multiple products. So that's sort of where, that was sort of my takeaway also from it. I think from barriers, I think, I think the incentive, first of all, the policy world is set up right now for algae. It is set up around biofuel. There has been a shift to look at biomaterials as well. But I do think that that's where most of the public funding is going. So I think to David's point, I think that's right. In terms of scale, I think it's time and it's technology still, right? I think there's still some barriers there around. And again, this is the phototrophic because we're on a different kind of technology path. But I think, and then third, I think it's, the idea of algae as a feedstock for animals. I'm not sure what the public perception is on that, but we may need to that may need to be something to be discussed in a public venue as well, and how people feel about that. Those
So
are sort of the
Jennifer,
three
just to
things,
follow
yeah.
up on your point, you think that the Chinese market would like this?
I think that, first I just was speaking about the demand for meat, but now if I can take a step back, and again, it comes off as self-promotion, but I manage a project here at the Wilson Center called Global Choke Point, and we've been looking at water, energy, food confrontations. We started U.S., but a lot of it, the work we've done is in China, and a big focus was looking at the water footprint of coal. I want more water in your talk too, because there's. But so that in China, we estimated that of all the water used in China, 20% of it goes to the coal sector, which is actually a lot smaller than the U.S. We use like 40% that once through. But that the work that we've been doing, we multimedia reports, lots of conversations like we do at the Wilson Center in China, and we've actually helped raise the issue of water, energy, and food nexus issue to, Chinese government. And last year, the U.S.-China Climate Agreement included the creation of a U.S.-China water energy research program. It's just going to be starting up. I guess the fiscal year starts soon if the budget keeps coming, right? But so they just wanted to let you know that there's, UC Berkeley is going to be leading the U.S. side. There'll be Chinese partners, and one of the areas of work, it's just interesting to me because you are kind of choke pointy the way I look at you, because you're talking about water, energy, food, nexus type issues, but that there is a big interest, and there's a lot of research going on, how to use brackish water, to produce energy. But think about that, when in the part where you're talking about energy, the water footprint of the coal, the water footprint of carbon capture, use, and sequestration, and how does algae stack up with that too? So that it just, keep water in mind, because water is something that it opens doors in conversations. Like when we go to China and talk about water, energy, nexus stuff, we say we're interested in the energy footprint on water, and they're like, you're interested in water. And so, so I think that I'm really curious to understand more, in your world too, about like, the impact. I mean, you use water, but it sounds like it's very efficient.
Yep.
And it doesn't, and the fact that you can use brackish and nasty water is quite appealing, because there's a lot of that around.
That's right. That's right. No, one thing that the model does, I think, doesn't do well enough yet is actually take into account the water savings when it comes to,
That's what I'd like to see.
as we approach agricultural intensification and the expansion of irrigation to sort of it's not saying much to say unprecedented, but actually, again, we're talking about several, maybe even order of magnitude for the expansion of irrigation worldwide by the end of the century. This is also an important point when you get all this land sparing. But then the question is, how much water are we going to need for these plantations when you're talking on the order of a billion hectares? So the replacement effects, it gets complicated quickly, I guess. Yeah, and there's a lot of room to improve there, especially as water relates to runoff and nitrogen cycles as well, and fertilizers.
So just I'll do one more question, then we can do Q&As. Just back to your point. I mean, you're right. I think you have this huge legacy system set up around biofuels.
Yep.
Right? And it's sort of policy, but it's also massive R&D investments.
Yeah.
And what do you think it would take to kind of nudge this over?
So it's ironic that actually this particular type of use for this feedstock doesn't require as much technology development as it would to just produce the infrastructure to produce algae. For biofuel systems, they're more complicated. You need to generate the algae, and the algae are engineered such that they have particular oil properties that make them more amenable to recover the algae, and then the or recover the oil. And the oil, you want to have certain properties so that it's more amenable to refining so that you can have it, produce a fuel. For the particular case, if you're just generating the biomass so that it can be used as animal feed, you avoid a lot of the, barriers that you were asking Jill about to how do you scale this, how do you develop this. A lot of those barriers are not there. And so really it's perhaps, the greater challenge is a re-education of people for them to look at this feedstock as an animal feed rather than a feedstock for biofuels, and have, the research looking into the carbon saving, carbon reducing power of it through this new lens, and that would redirect things and have the potential to bring this technology.
I mean, who do you think should be doing that?
Well, perhaps the Union of Concerned Scientists. I will, when this paper is published, I do plan to write about it, and these conversations have been taking place. The meeting you went to yesterday has, been a part of a longer series of people talking about the potential uses for algae. And so among people that are thinking about algae and its potential use for addressing climate change, this is not new news. So I guess the question is, how do you get it into the public sphere, and how do you get it, to transition? I think that's just a matter of time, papers like this, and then, trying to get press around reporting this and reframing it will change it. The other thing is, like, places like the Department of Energy recently have changed some of their funding structures and how they offer up funding announcements for projects to include things like co-products. And it's just a matter of, talking to the technology managers there and really getting them to, see research like this and then prioritize the mandates that they have for sustainability over the mandates they have to, contrive feedstocks into a biofuel pathway always. So we'll see.
Okay, let's have some questions. I think we have a mic that we can float around. Just raise your hand, we'll get you a mic, and just let us know who you are and where you're from. Yeah.
Thank you. Dan Borges, formerly with the Nature Conservancy. I was the Senior Policy Advisor for Water Resources. So I appreciate Jennifer's comments, and it is part of the presentation that I think would be valuable to have that discussion of water. And beyond the energy piece, agriculture itself is 65 to 80% of the water use. And again, you've talked about the runoff and pollution that's resulting from fertilizers and such. But I think that's a major discussion. And when you start thinking about barriers, probably my perception is colored by my activities on the Hill trying to support legislation related to water. You have to think about what interests currently are in that field of agriculture, whether it's Cargill or the big producers, and how do you get them behind something like this? Mm-hmm. Any comment?
So you're talking just make water a sort of a lead story there.
It helps. Look
Yeah.
at California.
Yeah. I think the water, and it's a nexus, water energy nexus.
Yeah.
We have another mic up there that we can share.
That's
out
right.
there.
Yeah, well, why don't you go, and then you could shift the mic over
Okay.
3 feet.
Okay, Rachel Goldstein with Mars. So after listening to the presentation and the discussion, I'll definitely look forward to reading the paper. But it's, I guess, a question of clarity. So during the presentation, it sounds, as I took away that the contribution to minimizing getting to 2 degrees C was more from a land use change in terms of increasing yields of the particular product of the algae on existing footprints rather than continuing to deforest. But the panel discussion was a little bit more, it sounded like with the autotrophic, of pulling carbon out of the atmosphere. So does the paper address both, and is one a bigger driver towards that goal than the other? I guess it wasn't clear from the 2 sets of discussions. Thank you.
So the algae, I mean, I'm assuming with high yields, I'm assuming closed system. So these are fed flue gas, and they're not just breathing, like open ponds. But I think at the end of the day, there's an energy cost to producing algae. It's far from zero, and it's probably higher than it even is to grow first and second generation biofuels, or to just grow a tree and burn it or something like that. So the algae itself is net carbon positive, but I think the important way to think about the conversation is actually how are we deploying our land resources? How do we do more with the dwindling amount, and certainly, especially in the context of soil degradation, of farm failure, as this may be a looming challenge, soil acidification. This is going to be an important part of it. How are we spending our land, and is that appropriately valued when you just deploy it as pasture?
Anyone else want to respond? It gets back to your co-production.
Yeah, yeah. I mean, I was curious with the because the technology for doing this is very simple, but are there certain, that you can have a technology, but then are there best practices, best management practices? I mean, I just don't know how. I wore green today, but I'm not an algae person. So I was just kind of curious. So it's not difficult to make, and
I would not say that. I would not say it's not difficult, and I've been given to understand that the challenges of scaling, especially with an autotrophic system, are enormous. I mean, it's not clear that that beyond a certain scale that you gain so much from expanding even further in terms of lowering the cost of productivity or something like that, or cost of productivity gains. But again, at a moment when the SDGs are sort of really the hot topic, and for the next years, very hopefully, there'll be a topic of fervent conversation. This algae is actually, from a systems perspective, the real challenge is avoiding problem shifting, and it's become clear that first and second generation biofuels are just shifting the problem for someone else. And Europe feels really good about its biofuel mandates, but until they see what it does to drive deforestation in Brazil and Indonesia and in the Congo Basin. And so the point here is that there's a potential to bring this all together in a nexus and avoid a choke
point.
point.
That in terms of, because it uses less land, so it's, I mean, right now I'm thinking China with the huge draw of soybeans from Venezuela, the U.S. and Brazil. But China could produce its own algae?
Well, China could, and it's also the case that, I mean, China, not just
so no shipping, diesel burning to ship all the
right.
soy.
I mean, Saudi can be producing its own because they're eating a lot of meat, but they're not growing a lot of feedstock. So and they're also burning a lot of coal and oil. So Saudi's got all the ingredients that you need, including the sunlight, for a phototrophic process. But China could do it as well. And in China, 10, 20 years hence, you may see enormous farms in China, such as they have been polluted by heavy metals, by soil acidification, by one thing after the next. And so this land will sit fallow, perfect spot to put algae.
So just to follow up on that a little bit, because I'm trying to get back to your point about where would you put R&D dollars, right?
Yeah.
I mean, do you see that as something you need to do more R&D on process optimization, or you've got the processes down and you've got to figure out how to go from kilotons to gigatons or whatever it is? I mean, is it a scaling issue now?
Yeah, so for Solazyme, we're in a slightly different position because we have a technology that is been pretty proven at this point. We use existing infrastructure when you think about, we use a fermentation-based technology. In fact, our pilot plant is a former Pabst Blue Ribbon brewery. I mean, that's the kind of technology we're using. So scale for us now is building more plants. It's not about the technology for us. So I know it's a little disjointed for the crowd here because this is fundamentally a different technology, but of course we need all these technologies to do, we need abundance, right? We don't need just one way to go. So I can't comment so well on the scale up of the autotrophic and phototrophic technology.
But feed as a co-product of a heterotrophic process is also an important part of to take out the oils first, maybe the most valuable part of it, and then recycle this. Obviously, Solazyme's realized there's a valuable product there, and to put it in context, in this kind of context is I think the value add there. Yeah.
Yeah. Exactly. That, again, we're making several products off of 1 acre of land.
I mean, do you think that actually that's the incentive, that key part of your business model, is actually you get really high-value stuff out? Could you create a business where you're just producing the protein, the algae? Because that's a waste product for you almost right now.
Right, so that's a good point. So I think that we think about it in 2 ways. One is that we are making the animal feed from the co-product, we don't call anything waste, right? Nothing goes to waste. The co-product of after we have extracted the oil from the algae, so it's all the leftover algae. We also make a protein, and that is a native algae that is kept whole. And in that case, the protein has the oil inside. The algal cell walls are made up of a great deal of protein. That is for human consumption. It could be used also for animal feed. So we actually can do both and, depending on the end market.
Let's go.
Hi, I wanted to thank you for the presentation. I'm Lark Williams from the Environmental Protection Agency. And I was interested how you viewed energy efficiency in the model and what sort of, how you accounted for that in increases in energy demand.
Mm-hmm. So I didn't show, but it's in the slides. Maybe the backup slides aren't there. But so because it's a linear differential equation model, it's pretty simple to just scale up or down all these individual parameters. And energy is one of them. So let me see if I can. So this is the listed on the left are different parameters that I scaled up and down. And in the case of energy demand, I looked at 0.25% annual increase or decrease in per capita energy demand moving forward, starting in 2010. And so that's a cumulative effect of about 20% up or down by the time you get to 2100. And so you can see energy demand is the fifth one here, and it does have an effect of about a 13 to 15% effect on the emission savings that we forecast. And so my energy the assumptions built into the energy are based on the global energy assessment that is a separate model, a separate EASA product, a different group. But those, I think, are regarded as leading estimates for different energy pathways and what our energy futures might look like. So these are, my error estimate is generally within a range set by some other effects, by some other body that's more specially focused, I guess.
We'll go over here and then back.
Hello. Okay. Hi, I'm Karen Peterson from the World Wildlife Fund, and I was hoping you could comment a little bit more on what you think the actual feasibility is of co-locating these plants on a scale that you're talking about, especially on marginal land, because I'm wondering how feasible that would be if you're needing both flue gas to provide the CO2 and wastewater, especially when you're thinking about the solar requirements and the water requirements.
I think it's not just coal plants. I mean, you can also, other industrial processes and certainly cement production is a significant source of carbon. And so at the beginning, I think actually when we begin to dive into this, you can see that algae is in fact a compelling transformation technology as to sort of drive a transformation of scale that I'm talking about from mostly fossil fuels to, fossil fuels is just a tiny portion, in that, the biomass production that I'm talking about in the first place, once you begin to, let's say that for every algae plant you build, you are freeing at least 10 times more land in terms of land that was previously gauged in the production of animal feed. And so as soon as this starts to happen, and as soon as you do begin to set up these biomass production plants, then burning a log is much dirtier than burning, in terms of carbon content, than burning a lump of coal, actually. So the concentration of carbon there is very significant, and all of a sudden you're not co-locating with simply power plants, but with these anywhere, you can co-locate anywhere within the 1 billion hectares of formerly agricultural land, which presumably, because we're not talking about land that's just subsistence farming, presumably is already well integrated into transport networks, into sort of distribution systems. And the other thing that I'll say is that CCS is going to be a part of our, certainly in America, this is a part of our energy future. And so we've already got this network of pipes and tubes to sort of deliver carbon to different places, to the nearest well or whatever, because liquefied carbon is used in drilling now. And so that network, it's just another network of pipes and tubes that we're going to be developing anyway. So to plug into that and use it in algae production is only an incremental increase. It's sort of, that infrastructure is actually part of our future already.
I guess I'm just more curious about co-locating with both. Any kind of energy source is going to provide the carbon dioxide and water, so the wastewater, especially if you're looking for a lot of solar radiation, you might be in an arid area where you might not have and I know like the development for brackish water algae is still like under development. So I guess I just think there are a lot of factors dealing with the scalability that aren't being addressed yet.
Yeah, that's right. I mean, but it's also the case that if you've got, when you're starting to replace this land, again, it's already integrated into production networks, so maybe it's already irrigated, or it's near to a farm where, you know, that's where this really valuable nitrogen and phosphorus and increasingly valuable fertilizers are going to be coming from in the first place. So it's not necessarily municipal wastewater, but agricultural runoff, if we can prevent that from going into the, you know, back into the Colorado River or whatever, but actually use algae, and this is already happening, to filter that wastewater and then, you know, go through a further downstream process. I mean, there's the point is just that this is replacing agricultural structures that are already in place in most cases, and so that's where we'd begin to develop the infrastructure.
Right here.
Hi, thank you for the talk. My name is Joe Chiara. I'm with a company called Muron Corporation. I understand it's a linear differential equation model, but it seems like there's a lot of opportunities for nonlinear effects to provide consequential, results. So how do you what's the delicacy of this model, given, the fact that nonlinear effects do happen, and many of the things that you showed had nonlinear curves in it anyway?
I mean, it's true that when you get to, even when you get to the carbon system, and radiative forcing is itself not a nonlinear process. So those sort of specialized bits are the model can handle that. But I think the question is really about the confidence with which I can forecast the gumption it takes to forecast 80, 90 years in the future. And that's certainly a valid point. But at the end of the day, I would say then we need to get in the details of what does business as usual look like, and define that as just what happens absent transformative change. And of course, transformative change is the only constant anyway. So it's anticipated and it's expected. And there are certainly things built in here, like I said, CCS at high efficiency, capture efficiencies would require electrification of the entire grid or all of energy consumption. So these things, they're sort of assumptions that are built in or implicit, but at the end of the day, I think it's useful to have this integrative baseline of, let's just assume that everything progresses and yet nothing does at the same time. Where are we then? And you don't have to look all the way to 2100 to see some really impressive consequences. You need only look as far as mid-century before things. In some cases, it's instructive when the model fails to close, when it goes off the rails, because I don't know if you noticed, but at one point with feed demand and high population projection, the demand's just not met anymore. And so things like that, these are certainly not directly correlated to a reality that I'm claiming is going to obtain, But at the very least, it's a signpost for us to start a conversation about what do we need to do.
Okay, one last question here, and then I'm going to just go down the panel, final comments.
Thank you. I'm an odd bod here. I'm a retired grass-fed beef farmer. And I'm really puzzled that you have not included in your calculations any recognition of the fact that we have too much carbon in the air and too little in the ground. We are badly in need of increasing the soil organic carbon. And I think that should be part of your calculations as to what is possible. And it has not received the attention it should by the public policy, but there are parts of the USDA that are doing a very good job. It's called GraceNet. You might take a look with them and see what they're finding. It's part of ARS, Agricultural Research Service. And I experienced on my own farm significant carbon sequestration just on one tiny retreat kind of farm in West Virginia. It was quite exciting. And it's also, I also like the question here from EPA person where she was asking about the energy efficiency of the system that you're thinking of. How does that energy efficiency for this system compare with the energy efficiency of corn-fed beef? It's corn-fed beef is just very energy inefficient. It's lower price because of various structural reasons and subsidies, but it's not it's not energy efficient by any means. You start with the mining of the ore that produces all those big machines and the fabrication and the production of machinery that you use on a corn farm and the operation of that machinery. Those things just go on. That's not efficient, and I don't know how this system. I think it seems very interesting to me, particularly being able to use brackish water. And that's
You're kind of assuming that the life cycle inputs into the cows, or?
Well, yeah, I mean, the cows, I mean, the point's taken about, what are we feeding cows, but at the end of the day, the amount of land that is required to address, we look at agricultural emissions in just one lump sum, and then, of course, separately, there's the different energies that go into that. So, I mean, I think it's only a marginal factor to talk about feeding a cow this versus that. And actually, I think a more direct point is, why don't we engage people to eat less of cow no matter what it's fed?
Well,
and of course,
I agree with that. I think that it's interesting that grass-fed meat is more satisfying in smaller quantities.
So let me, I think we're almost at the witching hour. Just go down the panel, just sort of, what do you think would be an interesting next step? I mean, obviously, you might be open to running different model assumptions. We talked about including water. Once the paper is published, get it out there. I mean, what would you recommend we do?
I mean, I think in terms of once the paper is published, there's additional work that would be interesting to do under different scenarios. I think the point that was raised earlier about just how likely is it for all of the stars to align is really challenging. I mean, this is, like I said from the very beginning, let's set aside the actual numbers that you came out with at the end and what you think the temperature will be at the end of the century. What this really shows is there needs to be a better discussion about how we incentivize the use of biomass and the production of it. I think it's of course, I always make this point that we need a price on carbon, and this would address some of the issues about how you make these things align. So you know, how could you incentivize the co-location of algae production at, you know, at sources of CO2 and, you know, various amounts of water? A price on carbon would do that. And it would also direct how that algae is used. So you could get a greater carbon credit price for producing algae that was used to displace animal feed, because it would have the benefits of freeing up agricultural land and having a greater impact. And you would get less credit for just displacing a little bit of petroleum from a fuel that you produce. So going forward, you know, more analysis needs to be done. And I think perhaps more analysis needs to be done around, you know, the carbon reduction and economic incentives that would be necessary to actually achieve the outcomes from this type of technology, so that you could begin to develop public policies and planning for actually establishing the infrastructure and the path forward to do this.
Jill, any ideas?
So I think what struck me with this paper was really the idea of what is the best use of an acre of land or hectare of land. And I think we don't ever look at our resources like that today, because, and you're looking multivariate, so we're looking at climate, we're looking at food, we're looking at animal feed, and we're looking about how do we, you know, reduce the destruction of forest land. And that's what I think I really take away with it, is that I know that we make products to try to really address, you know, specific solutions, but we haven't wrapped around some of the other elements that you were talking about, and that's what's really brought a lot to mind. So I think for a resource issue and a policy issue, I think it's expanding the way we think about how we use our land right now. I think World Wildlife Fund's doing a really good job on freeze the footprint. So if we freeze the footprint, what does that mean for what we have? So that's kind of where my mind has gone with this, and I'm not sure if there's a specific policy recommendation I would make, but that was really interesting to me.
Okay.
Yeah,
Jennifer?
I mean, just kind of following, you know, like, at the Wilson Center, we're a meeting machine, right? And I kind of think that when your paper's done, you know, come back and talk to us more, because, you know, I think the China Environment Forum Mafia, there are lots of different conversations that we could be having, because I do a lot on U.S.-China energy and climate cooperation. I also do food safety and food security, and you strangely cross both those in an intriguing way. But I feel like that there's, you know, not just having conversations here, but I mean, I could see that my folks at USDA, ERS, who do work with the Chinese on food production, that, I don't know, that you have to get these ideas out there and get to know people. At WWF, you were just, you know, there's you know, the protein team, right? You know, that look at the supply. They're doing projects in China on the food supply chain. We had them here a while back talking about chicken production. Yeah. And that, you know, so that there's WWF, and there's not as many organizations doing this in China, but it'd be good to kind of, you know, start getting into these kinds of, you know, meetings. I think WWF is going to have a food security game in November. Maybe we could toss you into that, you know. So you get to, I don't know.
We have an institutional, I don't know if you're, EASA produced all the data for the Living Forest report, actually. So our relationship with WWF.
Oh, you already got that. Good.
Well, no, I mean, I'll just, even that we don't have an agenda, so I don't want to be misconstrued, but we do have an institutional relationship there. Yeah.
Yeah, but no, but I mean, this is an intriguing idea, and you want to, and the whole thing is that, you know, to change, you got to start new conversations and come at it a different way. But more needs to be done on the water footprint.
Yeah.
Carbon capture, sequestration uses lots of water. So I got worrisome there, but we could talk later.
Okay, so there's some next steps.
Yeah, yeah, absolutely.
Okay, thank you very much. And you can hang around for a few
Yes,
minutes.
yeah, I'll be around
Okay.
for a few minutes.
And do you have any sense of when the paper's coming out?
No, unfortunately. I mean, I don't, actually.
All right, if we can model that
Yeah,
one.
yeah, yeah, I wish.
Okay, thank you, everybody.
Thanks.